Hello learners, we have already learned about simple linear regression. In this section we are going to learn about the estimation process or how we can estimate the parameters of simple linear regression model. The ordinary least square method is the most widely used method to estimate the regression equation. Carl Friedrich Gauss proposed the least squares method. The ordinary least squares method is a procedure for using sample data to find the estimated regression equation. The least square method provides an estimated regression equation that minimizes the sum of squared deviations between the observed values of the dependent variable y and the estimated values of the dependent variable, which is denoted by y hat. This least squares criteria is used to choose the equation that provides the best fit. Let the two variables x and y have n pairs of observations x1, y1, x2, y2 up to xn, yn. A pair of the regression line is obtained from the bivariate variable. The regression equation of y on x is yi hat equal to b0 plus b1 xi. Here b0 and b1 are the sample statistics which we are going to estimate. The sum of squared residuals is given by summation of e square equal to summation of yi minus yi hat square. Substituting yi hat equal to b0 plus b1 xi in the above expression, we get summation of e square equal to summation of yi minus b square minus b1 xi whole square. We need to minimize this expression to estimate the parameters. To minimize this expression, we have to take the partial derivatives with respect to b0 and b1 and set them equal to 0 and then solve. So, if we do so, we will get these equations. You can see in equation 2, we have taken the partial derivative of yi minus b0 minus b1 xi whole square with respect to b0, and what we get is minus 2 summation of yi minus b0 minus b1 xi, and we will set them equal to 0. And in the equation 3, we have taken the partial derivatives of the expression yi minus b0 minus b1 xi whole square with respect to b1, and what we get is minus 2 summation of xi yi minus b0 minus b1 xi, and we have set them equal to 0. Now dividing the equation 2 by 2 and summing each term individually, we get this expression. Okay, so which is minus summation of yi plus summation of b0 plus summation of b1 xi. We know summation of b0 equals to nb0 as we have n pairs of observations here. So now we will put the value of summation of b0 equal to nb0 in the next equation, and we will take this term, that is minus summation of yi, in the right hand side of the equation. So what we get? We get that in the left hand side we have nb0 plus summation of xi b1, and in the right side we have summation of yi. Now we will keep the term b0, only the term b0 in the left hand side of the equation, and the other terms we will move the other terms in the right hand side of the equation, and which we get is b0 equal to summation of yi by n minus b1 into summation of xi divided by n. So we will mark this equation as equation 4. So similar algebraic simplifications can be done for equation 3. So what we have done for equation 2 here, that we have divided the equation by 2 and summing each term. So for equation 3 we will do the same thing. We will divide the equation 3 by 2 and summing each term individually. And what it implies is that summation of xi b0 plus summation of xi whole square b1 equal to summation of xi yi. Now, if I use the equation 4 in this equation, that is, we are using the value of b0, what we obtained in equation 4 in this equation, we will get a simplified form like this, which is summation of xi, summation of yi divided by n plus summation of xi square divided by n into b1 plus summation of xi square into b1 equals to summation of xi yi. And I am giving this equation number 5. By rearranging the equation 5, what we obtain? We obtain that b1 equals to summation of xi yi minus summation of xi summation of yi divided by n, and we divide this whole expression by summation of xi square minus summation of xi square divided by n. So this is also an equivalent term of this term, so we can write any one of these, and we know that y bar equals to summation of yi divided by n and x bar equal to summation of xi by n. So using these terms of y bar and x bar in equation 4, we get that b0 equals to y bar minus b1 x bar. So here in equation 6, you can see that we have the formula for b1, and equation 7 we have the formula for b0. And here the b0 and b1 are the estimates which we are needed to estimate our regression equation or to determine our regression equation. Now look at the interpretation of slope and the intercept. We know the intercept term is b1. Then what is the interpretation of b1? b1 is the estimated change in the average value of y as a result of a 1 unit change in x. Interpretation of b0, which is the slope, it is the value of the dependent variable when the value of the independent variable is 0. It is of little significance, but the interpretation of beta 1 is of more significance. Now here you can see some measures of variation. The first one is total sum of squares. The total sum of squares is a measure of variation on the values of dependent variable around their mean value. So if we denote the dependent variable as y and independent variable x, actually we don't need the independent variable in the measures of variation here now. So if we denote the dependent variable y and independent variable x, the mean of dependent variable is y bar. So the total sum of square SST equal to summation of yi minus y bar whole square. Now look at the regression sum of squares. The regression sum of squares is the sum of the square differences between the predicted value of y, and we denote it by y hat, and the mean value of y, which we denote by y bar. So what is SSR? Regression sum of squares or SSR equal to summation of yi hat minus y bar whole square. Now look at the another measures of variation, which is error sum of squares. Error sum of squares, or SSE, is the sum of square deviations between the observed value of y and the predicted value of y. So SSE equal to summation of yi minus yi hat whole square. The relationship between SSR, SST and SSE is SST, which is the total sum of square, is equal to SSR plus SSE. Here SSR is the regression sum of square and SSE is the error sum of square. So regression sum of square is explainable and error sum of square is not explainable. The goodness of fit of a statistical model describes how well it fits a set of observations. After estimating the parameters and determining the least square regression line, we need to know how good is the fit of this line to the sample data. We need an index of goodness of fit, and in regression analysis, coefficient of determination is used for measuring the goodness of fit. So, by measuring the coefficient of determination, we can know how good is the fit of this line to the sample data. The coefficient of determination measures the strength of the association that exists between dependent variable y and independent variable x. In statistics, coefficient of determination is denoted by r square. So you can see this expression as capital R square in somewhere. So you can denote it as your own. You can denote it by small r square or capital R square. So this is a number actually. So what is coefficient of determination? Coefficient of determination is a number that determines the proportion of variation in y, which is explained by independent variable of the regression line. Okay, so the coefficient of determination r square is defined as r square equal to explained variation divided by total variation, which is equal to SSR divided by SST. And we know the relationship between the measures of variation, which was that SST equal to SSR plus SSE. Using this relationship, we can also write this like this, that is 1 minus SSE divided by SST. So we know what is SSE and SST, and we just write the equations here, or we write the expressions in this line. So the value of r square lies between 0 and 1. The greater value of r square implies better fitting of the model to the data. For example, r square equal to 0.74 implies that 74% of the total variation of y can be explained by the regression model, or also we can say that 74% of the total variation of dependent variable can be explained by the independent variable. Here are some merits and demerits of simple linear regression. First, look at the merits of simple linear regression. Simple linear regression works well irrespective of data size. And simple linear regression model gives information about the relevance of features. Although simple linear regression is a powerful tool, it has some demerits too. The greatest drawback or demerit of simple linear regression is that if the assumptions of simple linear regression are violated, then it provides biased or inefficient estimates. And results are strongly affected by outliers in simple linear regression. Simple linear regression assumes that all the variables are normally distributed. So when the variables are not normally distributed, we can't use simple linear regression at all.